I've spent most of my career in the field of materials and corrosion engineering. Over the last 30 years, I've been engaged in various aspects of materials technology, materials engineering, manufacturing, and then lately in the last 15 odd years, I've been in the industry, oil and gas industry, contributing to materials and corrosion engineering in particular. This presentation is slated for about 30 minutes of running through the slides that I have. Discussions will follow after that, probably 15 to 20 minutes of discussion. If it has to go longer, I have no issues with that. I would like it to be a very interactive session, so feel free to stop me wherever you think is appropriate and ask questions if you would like to. I have no problem with that. I must say that the objective of today's session was primarily to share with all in attendance my learning journey in the field of materials and corrosion engineering. Briefly touch upon what I did through my career, just so that if it does some similarity with what your others have been following, senior corrosion professionals, well, they'll acknowledge there have been many pitfalls, there have been many successes, there have been many roadblocks which opened up later. So I would say it's been a journey of learning, which I would like to share with everybody. I would like to take them through what I've done over my career. After that, I'd like to focus on materials and damage and corrosion damage, its impact on HSE and asset integrity. I'd like to also take you all through the typical corrosion management in the oil and gas industry, which essentially cuts across all kinds of production assets in upstream oil and gas in particular. I'd like to take you through what we do in the asset development phase and what we do in the asset operations phase. To begin with my journey as a materials and corrosion engineer, I started with a diploma in metallurgy way back in 1981. I did a 3-year diploma in metallurgy with the objective of assisting my father in the field of foundry engineering. We actually started a small foundry. I thought I'll go and manage the foundry after my diploma. And that's it. I'm a businessman with a cool thing. I got a business on foundry. But it turned out that 3 or 4 years down the line, I understood that my learning was not enough. I understood that the technology I used at that time was primitive. And we had to get out of this. I had to painfully close the foundry and then get on with skills development, equipping myself with more knowledge. And then further on, I chose to come to the UAE in 1990. Briefly, for 2 years, I was here working for an aluminum smelter. After that, I went back to India and I studied, did my undergraduate and postgraduate studies in materials engineering, following which I was, for a very brief period, I was with the Defense Metallurgical Research Laboratories and various science and technology development establishments affiliated to the Government of India. Was with the International Advanced Research Center for Powder Metallurgy and New Materials for about 3 years. And then I said, well, I want to get back to industry. So I came back to the UAE again in 1997. Since then, I've been here. Most of my time I've spent in the UAE with laboratories dealing with support to oil and gas industry, with oil and gas operators, including Abu Dhabi National Oil Company and Emirates National Oil Company. The Dragon Oil was one of the companies I worked with. Briefly, I also worked for Petronas for 2 years between 2015 and 2017. I'm back with ADNOC now as a senior corrosion engineer. I'm centered around 15 operating assets and sites, providing materials and corrosion related support. We contribute to all phases, both the development phase and the operating phase of an asset. Materials and corrosion damage mechanisms and the corrosion management part, I'll go through the slides. Feel free to stop me wherever you think I should delve more. As I mentioned, the session will be 30 minutes with 20 minutes of question answers if that's okay. As part of our ad hoc safety culture, I think I'll start with a small safety moment for all who have joined here. We believe that behavioral-based safety is a very important aspect. Our behavior influences our safety around us. HSE, talking about environmental conditions around us. Our attitude, our behaviors contribute to 90% of all HSE issues that we see. So critical errors can contribute to increasing the risk of failures and thereby contributing to major safety incidents. So I would say it's important to ensure we take certain precautions. For example, we don't take shortcuts, we don't be complacent, try not to be overconfident. We're all learning. Ignoring rules is a very important aspect. We should avoid ignoring rules because they are all designed to help us be safe and ensure the safety of everybody working with us. Poor attitude is something that's absolutely unacceptable. Now, you can have poor attitude from critical mental health conditions that you can see from time to time with anybody and everybody. If we feel we are unwell, we actually stop working. That would be the better thing to do than to work in an unsafe way. Some of the things that we do take care of, for example, is, we always keep our eyes on the task. We focus on what is the work on hand. We want our mind to be on the task as well. That's a very important aspect. We always avoid being the line of fire. For instance, if there's a lifting operation going on, we stay out of the line of fire. We don't stay right behind, below the load being lifted, to stay away. Similarly, taking care of yourself, balancing yourself, ensuring that you don't slip while you walk, while you negotiate difficult, access locations. We follow the rules. We have always safety braces. We use safety braces, safety gadgets in order to keep us arrested with the locations we are traversing or moving through, so that we do not slip and fall. With this, we'll now move on to the main topic here. We will talk briefly about corrosion basics. The objective here is not to take you through a whole lot of corrosion basics, but to just touch upon why is corrosion so important, and why is corrosion an important aspect for materials engineers in particular to deal with early in their career, because that's one of the most important things that affect integrity of assets. We'll also talk about the impact of corrosion on HSE, asset integrity, and business briefly. We'll touch upon corrosion science, technology, and engineering, which is a very important backbone to the development of sound corrosion management philosophy and practices. We'll talk about materials widely used in the oil and gas industry. We'll touch upon some of these materials just to talk about briefly about the economic aspects of materials. Then we talk about the application of materials. Briefly, we talk about damage mechanisms. I know there's quite a lot that's put on the screen here. We will just briefly touch upon these. The objective here is to give you an introduction. Maybe I could have another chance or several further sessions with the community at NTU to deal with separate aspects. Each aspect that's being discussed here, each of them have their own importance, and covering them in a 30-minute session is probably unrealistic. Let's do our best. This session will also talk about corrosion management in the asset development phase. We talk about material selection, design for corrosion control, corrosion-related project deliverables. We'll talk about corrosion management in an operating phase of an asset. We're talking about how we plan and execute and implement corrosion management in an oil and gas facility. We talk about performance reporting, which is an extremely important aspect of managing corrosion, because without data, without a reporting system in place, communication is a very important aspect. You need to communicate everything that you do in the site with respect to corrosion management in order to be able to reduce risk, mitigate risk, and thereby assure integrity of assets through the design life. Continuous improvement processes have to be in place. We learn from every single incident that we face in the field, be it an HSE incident. I'm talking about slips, falls, unfortunate accidents, unfortunate corrosion-related incidents like leaks, or even, when we talk about explosions, we talk about loss of containment incidents. We learn from each of those. So what do? We do root cause analysis. We share lessons learned across our group, across the industry, in order to keep the continuous improvement process on. Last but not least is the subject of change management. Mankind has always gone through several changes across centuries and centuries of history. How do we manage these changes? Not only in historical events, but also in the field, in our operating assets. When you have changes, how do you manage these changes such that the risk of damage, the risk of any incident happening is kept to an alert level, what we call as low as practically reasonable. Let's touch upon the corrosion basics. As you all would be familiar with, materials undergo several stages of processing before they become engineered materials. Engineered materials ranging from the simplest and most widely used material is probably carbon steel among the metallic materials. You've got a range of corrosion resistant alloys. You've got copper alloys, you've got titanium alloys, you've got nickel alloys, you've got nickel, cobalt, chromium, molybdenum alloys. And then you've got a range of non-metallic materials. You name it. There are ceramics, you've got composite materials, you've got advanced electronic materials, magnetic materials, you name it, there are a number of materials. Now, these materials get engineered in order to be applied in their fields. In doing so, as you all know from the law of thermodynamics, we are moving them from their lower state of energy. Therefore, there is always a tendency for them to revert by reacting with their environment unless they are engineered to be absolutely corrosion resistant. So we need to know that corrosion is a chemical or electrochemical reaction in definition between a material, usually a metallic material, and its environment, which causes deterioration or degradation of the material and its properties, therefore it impacts its performance. So how do we manage that? We'll see it in the slides that follow. Engineered materials and equipment suffer damage from different forms of corrosion. We'll just take you through a glimpse of some of the damages that we generally see in oil and gas industry, typically. What you see on the top left picture is a structural member of our offshore platforms. What you see is large diameter ranging from about 6 to 24-inch diameter pipe structural steels. They suffer from corrosion because of marine environmental exposure. There's corrosion occurring because of seawater and salty water depositing with oxygen present in the atmosphere. You have aqueous corrosion resulting in metal thinning and loss of structural integrity. On the top right picture, you see a material which has suffered cracking, and eventually under stress, it cracks and breaks, or it fractures. The two bottom pictures show how internal damage can occur in piping or pipeline materials. You can see to the bottom left, typical flow-assisted corrosion or erosion corrosion damage. To the bottom right, you see a typical localized pitting attack of the example here is a carbon steel pipe. So you can have corrosion by uniform corrosion, you can have corrosion by localized damage, you can have corrosion due to environmental assisted cracking mechanisms, you can have corrosion and damage because of flow assisted damage mechanisms. So aqueous corrosion is the most common form of corrosion we see, because most of the engineered materials subject to environmental exposure, where you encounter the presence of water in combination with air or oxygen, resulting in an environment that tends to be corrosive to particularly ferrous alloys. Non-ferrous alloys like copper-based alloys tend to develop a patina or a corrosion-resistant outer film that helps it retain its internal structure for a longer period of time. They tend to be they're expensive as well. So economics do not always permit us to use corrosion resistance alloys. We go with carbon steel and manage corrosion. There are some pictures of how corrosion manifests itself. On the top top right and the bottom right, you can see soil-based corrosion of carbon steel pipelines underground. On the bottom right, you see a picture of a subsea pipeline that's suffering damage from external corrosion. To the left of this picture is a typical electrochemical cell that explains how aqueous corrosion occurs, typically in the form of anodic dissolution of the metal. On one side, on the other side, you have reduction reactions occurring at the cathode. So this is a typical electrogalvanic or electrochemical reaction. Examples of atmospheric corrosion, where fasteners tend to corrode because their external surface coatings are damaged. They can result in disastrous failures of structures if the fasteners lose their ability to hold pieces of material together. Here is an example of internal corrosion again. As you see, pipe or pipeline materials tend to carry fluids. I mean, they're designed to carry fluids. It could be either in oil and gas business, it's either oil, gas, water, or a combination of the three, which we call as well fluids or multi-phase fluids. You can have deposition of brine-based scaling products, or you can have deposition of bacterial bacterial microbiological growth, which results in slimes and deposits of bacteria which thicken over time and cause undeposit microbiological corrosion. To then run you through what the impacts of corrosion on HSE, asset integrity and business, needless to say, corrosion results in major issues in oil and gas business particularly. You can have loss of pressure containment. It's a very important aspect. If you have loss of pressure containment or a leak, you have possibly toxic, aggressive, hazardous fluids passing into the environment, which can result in either safety risk to personnel or can result in damage to the environment in terms of, if it's a subsea pipeline, you can imagine how a toxic H2S laden crude, if it's released into the sea, can cause major damage to biological life in the sea and possibly cause irreparable damage to life forms. So That's a very important aspect. The second most important, I think, from an oil and gas perspective is contamination of process fluids. We have a number of equipment that work on heat exchange, which means you've got heat exchangers, you've got heaters. If you've got contamination of one side, either the process side or the cooling side or a fire heater, you've got the fuel and the fire side and the process side. If there is cross-contamination, you can have aggressive corrosion occurring on either of the two. In addition, you can have serious process upsets, quality issues with the process. So contamination of process fluids can result from corrosion, and they can have serious consequential damage. Loss of integrity, as we talked about, oil and gas facilities are very expensive to build, and they're built with an intent of realizing economic benefit through a design life period, usually ranging from 30, 35, 40 years, in some cases beyond. So what I would say is that loss of integrity is a very important aspect to address. Financial losses, very, very important. Reputation, also as important. Just to touch upon the cost of corrosion. The cost of corrosion across the globe about 8 years ago was surveyed and was estimated to be about 3.4% of the global GDP, touching about $2 trillion a year. So that's something that we need to note, that corrosion engineering by itself is sort of less attractive in that it doesn't provide value in terms of a production target, but it does have a serious impact on the bottom line of companies, because it reduces the cost of operation. Cost of losses are reduced because of corrosion engineering. So it is a very, very important aspect. As you can see here, it's $2 trillion a year of potential cost to the economy, which we as corrosion engineers help reduce. Corrosion science and technology and engineering is a subject that I wanted to touch upon here today, because I'm speaking to a very august gathering, the academia, the students of NTU, who are the future leaders of tomorrow. I think it's very important that we emphasize the importance of science, technology, and engineering to the field of oil and gas materials and corrosion. Universities have a very important role to play. They need to embed the knowledge that currently exists within the industry. That is one of the reasons why I thought I should, at this point in time, share my experience, probably through this and many more sessions. I'm open to speak to you all on various subjects within the oil and gas, within the materials domain. Sharing my knowledge doesn't cost me anything. It gives me great pleasure, and I would be happy to collaborate with any and all students in NTU. I would be happy to collaborate with professors, with the academia, the doctoral, postdoctoral students as well. My knowledge is limited, but then I have some specialized experiences which I can certainly bring to the table, and I'm willing to do that at any time. There are a number of universities offering materials and corrosion engineering. Corrosion engineering is a sort of a niche area, in that not many institutions offer it at the undergraduate levels. I've heard of only a few. At the postgraduate, at the doctoral level and beyond, the number of universities offering. And I'm happy that I'm in a position to speak to you all today. We as ADNOC and other oil companies that I've been in service with before, we collaborate closely with universities, provide internships to support to students. We also provide support to research and development efforts, whether it be joint industry projects or research and development laboratories, where we pass our problems and get them solved. So we are willing to collaborate. Materials and corrosion testing laboratories form a very important part of the learning with respect to learning about materials and corrosion, especially with respect to materials failure assessments or degradation assessments, failure investigations, root cause analysis, and so on. Professional societies like the ASM International on materials, you've got the Institute of Materials, UK, you've got a number of international, the Japanese Institute of Materials, you've got a number of materials organizations within India as well. I'm a member of at least 2 of them, as I know, in India, which provide a lot of support to the industry. We have the Association of Materials Protection and Performance, which is a combination of NACE International, SSPC. We've got the International Corrosion Society. We've got the European Federation of Corrosion. A number of supporting materials-related institutions include the American Welding Society, the Society for Non-Destructive Testing, for Mechanical Engineering, the ASME, Petroleum, the American Petroleum Institute, a number of others who provide opportunities for learning for students, so you can become a student member and take this learning journey. You know, you can catch the baton early in your career and carry it through. So I would encourage you all to become student members and take it on. Corrosion technology, well, ample opportunity in materials, metals, alloys, non-metals, ceramics, composites, you name it. There's a lot of materials, engineered materials that one can work on. I'm very sure NTU is doing well. Welding and joining is a very important area of both industry knowledge as well as research opportunities. Joining technologies require a lot of input from research establishments and universities possibly. Surface modification, laser modification, diffusion coatings, name it. You've got protective coatings and linings, larger thicknesses. You've got non-metallic coatings. You've got advanced metallic linings, alloy linings. You've got chemical treatment processes, which range from chemical treatment for corrosion mitigation, chemical treatment to change the environment and keep it or make it less corrosive. You've got cathodic protection technologies, corrosion monitoring technologies. Inspection is a very, very important field, which follows up on corrosion management, as an integrity management tool. Inspection tells us what is the real condition of our asset, helps us find ways and means of improving corrosion management. Data analysis, no doubt, is the backbone of all that we do. So today's big data management, data science, artificial intelligence, anything that you can bring to the table will help us manage corrosion better. Corrosion engineering, you all know about it. Just touch upon, it is important to understand materials, their properties and behavior. We use this extensively in oil and gas. We understand the behavior of materials more from applying it than just testing it. When we apply it, we learn how unpredictable I would say how estimated predicted conditions can be different, causing damage to materials. We learn from it, and we then input that into lessons learned aspect. We bring it up for future science R&D for us to improve. Corrosion technologies, there are many corrosion control technologies that one can work on. You've got coating technologies, you've got material design and development technologies. We've got technologies around chemical treatment, development of corrosion inhibitors, testing of corrosion inhibitors, development of advanced corrosion inhibitors for high temperature application, for high temperature and pressure wells, and so on. Corrosion monitoring technologies, we normally rely on NDT as an inspection methodology, but today we are looking at proactive corrosion control, which means what we do is we have advanced either non-destructive tools or in situ or intrusive corrosion monitoring devices installed in our systems, which tell us how our control is working. If there are deviations from the control criteria, we're able to take the recourse as fast as we can in order to bring about some important proactive corrosion control. Engineering solutions for corrosion problems. That's a very important aspect. Corrosion problems, for example, in the upstream business that I serve, it's only a prediction as to what's coming out of the reservoir. Based on this prediction, we design the facilities, including selection of materials and corrosion control philosophy. We implement them. In the early phase of an asset life, you need to check what's changing from the original predicted or estimated parameters of the fluids coming from the reservoir. And you need to take early action, solve problems possibly before they become beyond our control. So many of these things help us manage very, very costly assets and therefore ensure integrity of the assets and return on investment for the shareholders who hold these companies. So the bottom line is we need to ensure integrity across the design line.